When you hear the word embossing, you probably picture, I don't know, a fancy stamp on a wedding invitation, right? But what if that same basic idea is the secret behind some of the most advanced tech we use every single day? We're talking about everything from your phone's camera to cutting-edge medical tests. Yep, believe it or not, it all comes back to embossing.
So really, what could these two things possibly have in common? I mean, one captures light, the other analyzes tiny drops of fluid. They feel like they're from completely different universes. But the secret sauce, the thing that connects them, is a manufacturing process that's gotten unbelievably sophisticated. It's all about shaping materials at a scale you can barely even imagine.
So let's break it down. At its heart, embossing is pretty simple. It's the art and science of creating these three-dimensional patterns on a surface. Think of it like taking something totally flat and giving it a new, super precise and often microscopic shape, and you do it all with a careful mix of pressure and energy. Okay, so the basic concept, it's actually really straightforward. You've got a mold, like a stamp, you have your material that you can shape, and then you apply some kind of force or energy. And voila, you get a perfect replica. Sounds easy enough, right? But what happens when that force and energy isn't just a simple press? What if it involves lasers or sound waves or even crazy powerful magnetic fields? Well, that's where things get really cool.
So let's dive into that modern forging toolkit, because trust me, we have come a long, long way from just a simple mechanical press.
See, the name of the game here is precision. To make these tiny microscopic structures, you can't just, push harder. That would just break everything. Instead, you need smarter, more elegant ways to apply energy. It's more like persuading the material into the exact shape you want, down to the nanometer. And this modern toolkit uses a whole spectrum of energy sources. We can use intense heat in a process called hot embossing, which is just perfect for making those tiny little channels you'd find in a lab on a chip. Or how about this? We can use sound. Ultrasonic vibrations actually help a material settle perfectly into a mold, and crucially, keep it from springing back out of shape. We can even use incredibly powerful magnetic fields to form thin metal sheets in just a flash. And this is not just trial and error, The science here is incredibly deep. For example, scientists use something called the Blaha effect. Now, to put it simply, this means that if you hit a material with super high-frequency sound waves, it can temporarily act more like soft putty. It becomes way easier to shape. This little trick is what lets them get these absolutely stunning levels of detail at the micro level. And then, of course, you've got lasers. You can use them to etch unbelievably detailed molds with just pinpoint accuracy. Or you can even skip the mold entirely. There's a technique called laser shock imprinting, where the raw power of the laser is used to basically blast a pattern directly onto the material itself. Wild, right? But, all these amazing tools are pretty useless if you don't have the right canvas to work on. And the range of materials that we can now emboss, it's just mind-blowing.
I mean, we're not just talking about the usual suspects here, like plastics and metals. Today's embossing canvas includes things like glass, Teflon, and even advanced composites that are reinforced with natural stuff, like coconut fibers. Researchers are even figuring out how to precisely emboss leather to give it better shape and make it more durable. It's incredible.
And this number right here, this just perfectly illustrates the scale we're talking about, 80 nanometers. That is the size of tiny pillars that can be formed on a polymer using hot embossing. To give you some perspective, a single human hair is about 80,000 nanometers wide. We are literally talking about creating structures that are smaller than a virus. And that right there, that is the key. It's all about versatility. The fact that we can apply these super precise patterns to almost any material you can think of, well, that's what unlocks the door to solving some really huge real-world problems. So what's the big payoff here? Why are we going through all this trouble to make tiny little bumps on things? Well, because these microscopic patterns are having an absolutely massive impact on the world around us. Let's start with optics. Remember that question I asked at the beginning about your phone's camera? Well, the lens in there is almost certainly covered in a microscopic embossed pattern. It's called a microlens array, and it helps focus light with incredible efficiency. Other patterns can create anti-reflective surfaces, just like the ones on high-end glasses. And then you have medicine, with those incredible lab-on-a-chip devices. By embossing these tiny channels onto a simple polymer chip, you can run complex medical tests with just a single drop of blood. You get results in minutes instead of days. I mean, this is completely revolutionizing diagnostics. The impact even extends to energy, and this is huge. Embossing patterns onto battery parts can dramatically increase their surface area, which makes them way more efficient. The same idea applies to solar power, where embossed lenses, called Fresnel lenses, can concentrate sunlight to generate way more electricity from the same panel.
A lot of the magic behind this comes down to one really simple principle: surface area. Think about it. By taking a flat surface and giving it a micro or even a nanostructure, you massively increase the area that's available to do work. So more surface area means more chemical reactions for a battery or more light being captured by a solar cell. It's a game changer.
But how on earth do engineers get these microscopic patterns so perfectly every single time? It's not just about building a better machine, it's about the brains of the operation.
You know, back in the day, getting this stuff right was all trial and error. It was slow, it was super expensive, and the results were unpredictable. But today, we use powerful digital simulations like finite element modeling. These let us predict exactly how a material is going to flow and bend and stretch before we ever make a single physical tool. We're even moving towards something called a digital twin. This is so cool. It's a complete virtual copy of the physical embossing machine running in a computer. It takes in real-time data from sensors on the factory floor and uses it to constantly update and optimize the process, live. It's really the ultimate fusion of the digital and the physical worlds.
And this whole digital side of things is a suite of incredibly sophisticated tools. Engineers use all these advanced algorithms and methods to crunch massive amounts of data. And what they're looking for is the absolute perfect recipe, the optimal settings for temperature, for pressure, for time, for any material and any pattern they're working with.
So the crucial point here is modern embossing is just as much about data and simulation as it is about physical force. It's really this beautiful dance between powerful machines and intelligent algorithms, and together they're achieving results that were frankly just science fiction a few years ago.
Which, of course, leaves us with one final and pretty exciting question. We can now shape almost any material with nanoscale precision, and we're guided by these incredibly smart simulations. So, with tools this powerful in our hands, what on earth are we going to shape next?